example based on Lenz's law and Faraday's law. This is one of the example. See, this is a current carrying conductor is given, having current I. This is a long conductor. Now we are having three loops. This is your loop number 1. This is your loop number 2. And this is a loop number 3. Now the question is this: if the loop is moving parallel to conductor with velocity v, loop 2 is moving and loop 3 is moving towards the conductor with velocity v like this. This is the question here. It is a long current carrying conductor having current I. There are 3 loops, 1, 2, 3. All are identical loops, suppose. Loop 1 is moving parallel to conductor, loop 2 away from the conductor, loop 3 towards the conductor. Now, find the induced current direction. Induced current direction on each loop. This is the question here. Very basic question related to your Lenz's law. So first of all, we will see कि either there is a current or not. So that we can get, the first we have to check it कि either there is an induced EMF or not. So induced EMF is developed only when there is change in flux. Now, if I am talking about the first loop is moving parallel to the conductor. So although there is a flux in the loop first, but every point either here always remain at same distance from the conductor. So whatever flux in the loop 1, that will not change. Even it is moving in this direction because it is moving parallel to conductor, so different part of the loop will be always at same distance from the conductor. So flux through the first loop will remain constant. So first part, the flux through first loop will remain constant, So there is no induced EMF. No induced EMF, so no induced current. So this is the answer of first part or first loop. Second, if I am talking about the second loop, as second loop is moving away from the conductor, so different part of the loop are moving at larger distance as it proceeds. So magnetic field associated with this loop will decrease. If magnetic field will decrease, the flux is decreasing. So in the second we can say flux is decreasing. Flux is decreasing because magnetic field is decreasing. Magnetic field is decreasing in different part of the loop. In different part of loop, flux is decreasing because magnetic field is decreasing in different part of loop. Now, although magnetic flux is decreasing, but we have to check it if flux is decreasing because of magnetic field decreasing. So according to Lenz law, the induced current will be in such a manner it will try to maintain the same flux. So to maintain the same flux, we should have same magnetic field as it was earlier. So check it. What is the direction of magnetic field? Due to this current carrying conductor, direction of magnetic field is inward. It means if I am talking about here, the field is your inward. And as it moves away from the conductor, that field you are decreasing, means inward field you are decreasing. So to increase the inward field, what is required? A clockwise current is required. So the induced current will be clockwise. So to increase inward field, clockwise current is required. Clockwise current required. So induced current in the loop will be clockwise. Similarly, in the third, just opposite case of second, here field is also your inward, but conductor is moving closer, that field your increases. So to decrease that field, the field should be produced by the induced current in your outward direction. So outward field will be your because of anti-clockwise current. So third, just opposite case of second. Just opposite case of second. So here anti-clockwise current. Anti-clockwise current. So this is the one of the example. Now see another example. In this example, that we are having two loops. In one of the loop, galvanometer is connected, and near to that another loop we are having. In this, a battery is there with the help of the switch S. So now we have to find the current in the loop. Let this is the loop number 1 and loop number 2. So question is that find the current in loop 1 when switch of loop 2 closed and reopen. See the solution. First of all, when the switch S was open, there was no current in the loop 2 because circuit was not connected. Now, as soon as the switch S close, immediately current start flowing in the clockwise direction. When current start flowing in the clockwise direction, so this current I will take some time to get stabilized. See, due to this current, if I am looking the magnetic field direction, the magnetic field here inward, the lines of forces will go like this. So if this is just simply loop here, the lines of forces will go inside and it will come out like this, in this manner. So due to the effect of this current I, magnetic field lines will be inward into the loop 2 and that will come out to the loop 1 like this. The magnetic field direction will be this. And now, as current I is increasing, this B value also increases. Earlier, when the switch S was open, no current was there. Now, as soon as switch is closed, current I start increasing. B value in outward magnetic field increases. So, flux associated with the loop 1 increases. So, as flux increases, according to Lenz's law, so that current, induced current in the loop 1 will be such that it will try to maintain the same flux. So, it will try to reduce that field. To reduce the field, so field should be inward by the induced current. If current is your clockwise, then the field will be your inward. So, we can say in the first part, when switch S close, at that moment induced current in the loop 1 will be clockwise. Induced current in the loop 1 will be clockwise. Now, when switch S reopen, now see the important point here. See another diagram here. Switch S is there. Current is I here. And this is loop 2. And this is your loop 1. At this time, when switch is closed here, current I is here. And current I here, the magnetic field your inward. And here your field your outward. Here field your outward. That field your stabilized field. It means constant field. So now the flux in the loop 2 is your, in the flux in the loop 1 your constant. As soon as switch S reopen, the current I this start your decreasing. So due to effect of that decreasing current, B value decreases. B value decreases. So now again induced current will be such that it will try to maintain the same B. So it will try to add that B. So current in that will be your in anti-clockwise direction. So we can write as switch S reopen. So current in the loop 2. So current in the loop 2 decreases, and that decreases the flux in the loop 1. That decreases flux in loop 1. So induced current in the loop 1 will be, so induced current in loop 1 will be anti-clockwise. So this is the another example of Lenz's law. Now see one another example. So now see here, MNOP is a square loop of area 2 meter square having resistance 10 ohm is kept in time varying magnetic field B is equal to 2t square minus 2t plus 1. Find the direction and magnitude of induced current in the loop. Induced current in the loop at t is equal to 2 seconds. This is the problem here. Direction and magnitude of induced current in the loop at t is equal to 2 seconds. See that. First of all, we will find here how much the EMF at t is equal to 2 seconds, and then current we can get by EMF by resistance. See, induced current I is equal to induced EMF by resistance, and this we can write 1 by R d phi by dt. See here, see I is equal to here 1 by R value given 10 ohm, so 1 by 10, d phi by dt means area into dV by dt. So area into dV by dt. So now area given here 2 meter square. So this 2 by 10 become your 1 by 5. Now see the dV by dt. Just differentiate this one. 4t minus 2. 4t minus 2. And this they are asking at t is equal to 2 seconds. So t is 2 seconds if I am putting here. So this become your 6 by 5. The 6 by 5 ampere is the current. This is no problem at all. So current value is 6 by 5 ampere. But main point is what is the direction of current? So direction of current means as per the Lenz law here, why the flux is changing? Flux is changing because of the magnetic field is changing. And magnetic field here, we would like to check it. At t is equal to 2 seconds, magnetic field here increasing or decreasing. So for that we will find dV by dt. dV by dt as we have found here 4t minus 2. This is dV by dt, and this value we are looking for t is equal to 2. T is equal to 2 seconds, it comes your 6. So that gives us a rate of change of magnetic field here 6 means positive. The positive means magnetic field here increasing, the inward magnetic field here increasing. Inward magnetic field here increasing, so current, induced current will be such that it will try to decrease that magnetic field. To decrease the magnetic field should be your opposite to that. Opposite means outward direction. For that, current should be your anti-clockwise direction. So this is the direction of current, and magnitude of current your 6 by 5 ampere. So in this manner we can solve the problem based on this. Let's see another example. See the example 4. MNOP is a rectangular loop of area 2 meters square is kept in uniform magnetic field 2 Tesla directed into the plane of loop as shown in diagram. The resistance of loop, if the resistance of loop is 10 ohm, find the average flux or average EMF induced in the loop if the loop is rotated by 180 degree about given axis in 0.01 second. This is the question here. Now see the solution. So question is that MNOP is a loop. MNOP is a loop which is kept in uniform magnetic field 2 Tesla. Area is 2 meters square. So now this loop is rotate about this axis by an angle 180 in 0.01 second. So they are asking how much the average EMF develop, as well as they can ask, see one more we can add, as well as find the amount of charge flown in this time. This also can be asked. So anything if they are asking we can calculate. So first thing is that as we know induced EMF is d phi by dt, rate of change of flux, or we can say average induced EMF. E average is nothing delta phi by delta t, and change in flux per second, that is the average EMF. So see, right now if I am calculating this flux, magnetic field your inward, area vector your outward. So delta phi is nothing. This we can say final flux minus initial flux by delta t. See, right now initial flux, area vector this side, magnetic field inward. So angle between the area vector and magnetic field your 180. So cos 180 or negative. So right now initial flux is your 2 into 2 4 and a minus 4 Weber. Now when it rotates by angle 180, it means just like my palm, right now palm is your towards outside. When it rotates by an angle 180, then palm will be inside. The area vector goes inside. Magnetic field will be also inside. Then the flux, final flux is also your same magnitude, but this is your positive value. Final flux your 4 Weber. Now the E average. E average, final your 4 minus initial is also your minus 4 to plus 4, and this happened in how much time? 0.01 second. So this is your 0.01. We can say 800 volt. So this is the induced EMF in this time. Now if they are asking the charge, so for charge, see, for charge we have found here delta Q is your I into delta T, and I is your induced EMF by resistance. The induced EMF is delta phi by delta T or delta phi by R. The change in flux by R, and change in flux already we have calculated, which is equal to your 4 plus 4 in 8, and resistance value your 10. Already it is given. So this is your 8 by 10 is 0.8 coulomb. This is the charge flown through this loop in one rotation. This is one of the example.